Hi, I'm Craig London. I'm here to introduce Bitware's StreamSurge network load test. Well, appliance is somewhat grandiose. It's a bitstream, and we're making it available for selected Bitware FPGA cards. So I'm going to go through some slides describing what it is, and then we're going to do a demo. And the demo's here in the lab using those boards there. Why does the world need an FPGA to implement a load tester? Software solutions running on commodity Intel servers are great for all kinds of protocol testing at any bandwidth. And they work for load testing as well. Gigabit Ethernet's pretty easy. 10 gigabit Ethernet load testing in software does require some heroics on the software engineer's part, but you can get it to work. 25 gigabit, I've not seen that in load testing yet. Anything above 25 is probably impossible. So an FPGA is what pretty much everyone turns to build a load testing gadget from 25 to, well, I guess the highest these days is 400 gigabit Ethernet. There are two different implementation strategies. I think most people do that, implement it with a line rate packet generator inside the FPGA. Then you can turn the packets around and check them, make sure they all arrive. An alternative is to actually include a very large memory buffer, which can play out arbitrary packets at line rate in various different patterns. It's this second strategy that we implemented. It lets you move more of the implementation details to the host. You can buy network testing appliances, so why would Bitware invent its own? Well, as you go up to higher bandwidths, like 100 gigabit Ethernet, there are fewer vendors, and the appliances tend to be very high functionality. Ixia, Spirent, Xena, we actually own one of these things. But at 100 gigabit, it's too costly to buy multiple copies to use everywhere. Specifically, we wanted extra copies in order to use in our continuous integration pipeline. People check in engineering changes overnight, they build and test. Also, there's a few places in the manufacturing floor we'd like to have packet generation and testing. We felt it was easier just to build something which had just the functionality we needed and nothing more than to buy more expensive appliances. We've decided to make the first release of what we did available to interesting customers, and we're not charging for the bitstream. If you want the source, we'll make that available to you as well, but we did use some third-party IP, and for the source to be useful to you, you're going to have to buy that third-party IP. So what exactly did we do? We started with Bitware's BitMartynuk shell, which is an implementation in an FPGA of a traditional NIC. Ethernet in, packets go to the host. This particular BitMartynuk shell uses DPDK for OS bypass on the host. To this, we added a memory buffer. It uses two banks of DDR to buffer 100 gigabit Ethernet in a FIFO-like in-out configuration. Then to that buffer, we added some functions. We added the ability to pause transmit so that the buffer can fill up. That way you can unpause it and you can spit out at line speed. We added the ability to loop the transmit buffer for infinitely long load tests. We added the ability to change the interframe gaps on transmit so that it doesn't have to be line rate. Maybe line rate breaks whatever it is you're building, and you want to see how big an interframe gap you can tolerate before it breaks. Also, we added the ability to apply transmit timestamps to the packet payloads. Then, when the packet comes back, we already had a timestamp on receive. Subtract the two, and you can basically measure the latency of how long it was outside the FPGA card, so you can measure latency and jitter. To make all that FPGA hardware work, we wrote our own DPDK application that we call StreamCLI. It's a command line, and it controls all the hardware functions that were described on the previous slides. In addition, it can receive packets into PCAP files, it can transmit PCAP files, it can fill the packet buffer with patterns that are based on the two Ethernet testing standards that are listed on the slide. It's the nature of the FPGA world that you need a different bit stream for each configuration. So as the standard download configuration, we've decided to make available a single 100 gig port implementation. It uses our XUP-P3R card that has a VU9P on it, speed grade 2. And it needs, for that DRAM buffer, at least 2 of the DIMMs on the board inserted, and they have to be 16 gigabyte DIMMs. If you have a different kind of board, different kind of DIMM configuration, it's possible for us to build you a bit stream, but it does involve work and it does involve a conversation. So give us a call. As I said before, this is a DPDK-based board, and our StreamCLI command is a DPDK application. What all of this means is any other DPDK-based network test software should, with some modification, just run on our board. We've got package N DPDK from Intel up and running, and we're looking at the others here. The simple demo you're about to see measures the latency of an Ethernet cable. But you could measure the latency of any packet obstacle course you can imagine. In the diagram, the lower board launches a packet into the network that has a timestamp in its payload. That packet traverses the network, again in this case it's a cable, gets to the upper board where the packet is timestamped on the way in. The 2 timestamps flow to the host where math can tell you the latency and multiple packets can tell you the jitter. Because we're using 2 boards, that means 2 separate clocks, and the unit in measurement here is often nanoseconds when you talk about a cable. You need to carefully synchronize the clocks between the 2 boards, and we use a GPS satellite for that. There's coaxes on the board for 10 megahertz and 1 PPS. So let's watch.
Hi, I'm Dennis with Bitware, and we are going to demonstrate the StreamCLI applications. We have 2 XUP-P3R boards connected to each other. We'll start by getting the first board ready to receive packets, and we will tell it where to look inside the packet for where to expect to find the transmitted timestamp in the payload of the packet. Let's see, 32. We will insert the timestamp at offset 32 in the packet. We'll switch to the other board. And send packets, and we'll send 10 packets of length 128 with the timestamp inserted at 32. And you can see here we got roughly around 62 maybe average latency, and this is measuring the path from the Xilinx CMAC transmit, which does the timestamp insertion, to the other card, which also through Bitware IP captures the receive timestamp. The receipt of the packet is all you need to calculate the latency of the trip. And we are able to coordinate the clocks of the 2 boards by using a PPS signal generated off-board by a time base. And we can look at how close the clocks are in sync. And due to the onboard oscillator, we see a slight variation of a few nanoseconds, but when measuring network latency, that's often marginal. So we can also measure the latency of a switch by connecting, instead of the boards directly to one another, we can also connect them through the switch and set up L2 filtering and measure the path that way as well. So this is just one of the features of StreamSurge. It also has features such as very large transmit FIFO for blasting out packets at line rate, L2 filtering, and SDNet, and RSS.